This is select sections from Chapter 2 of your textbook, and it will focus on the history of atomic models and the subatomic particles that make up an atom, and the difference between isotopes and ions, and then kind of a quick overview of the periodic table. So, talking about history of the atomic model, it's come a long ways. This amazes me, actually. In the early 1800s, a man named Dalton suggested that all matter is made up of these little invisible, because they're so small, little billiard ball particles, and which is incredibly insightful if you think about how long ago that was. And then you'll see as we go through it that the first subatomic particle was discovered, and then the nucleus was discovered. And we won't talk about the more recent models of the atom until later on. So again, the first subatomic particle to be discovered was the electron. It was discovered by a scientist named J.J. Thomson. And basically what he did is he took a cathode ray tube. That used to be how TVs were lit up. I actually am old enough I remember that. But basically, a cathode ray tube has charged metal plates that create a current, and it's under vacuum. Well, not total vacuum, but it has, you can put whatever gas you want in it, and the metal plates can be any metal. And he discovered that regardless of the gas that he put in the cathode ray tube, and regardless of the metal composition of the metal plates, that all of these materials produced a negatively charged particles. And he knew they were negatively charged because as they traveled through the cathode ray tube, they bent toward the positively charged plates. So eventually, with enough work, he discovered that all types of materials produce these, and so he decided it was a fundamental part of all matter, and it eventually ended up being identified as the electron. Then there was a scientist named Millikan who figured out the exact charge and mass of an electron. It's kind of amazing. They call that the oil drop experiment. And basically, he aerosolized or atomized oil droplets, and then measured the charge of each droplet. And it turned out that each droplet was a multiple of the same charge, depending on the size of the droplet, how many electrons it would have in it. But he found the lowest common denominator, basically, of the charge of all the drops, and that was the charge of an electron. So Thomson, after he discovered the electron, he didn't know about the nucleus or any other subatomic particle, so he just theorized that an atom was made up of these negatively charged electrons, which were distributed throughout some overall positively charged sphere, which is not true, but we call that the plum pudding model. It looks more like a chocolate chip cookie these days, but they called it plum pudding back then. So then along came Rutherford, who, a scientist, I believe he actually studied under Thomson, and he actually set out to duplicate or confirm or validate Thomson's model. It turns out he refuted it. So what he did is he took a piece of thin gold foil, and as all objects, all pieces of matter are made up of atoms, right? And so the gold foil just had a bunch of gold atoms, and nothing else. So he he was working, I think, in radioactive area anyway. So he shot a radioactive particle called an alpha particle, which was positively charged. He shot that at the gold foil, and he expected that it might be deflected a little, not much. And it turns out that most of the time, the vast majority of the time, the alpha particles went straight through that gold foil. It's like there wasn't anything there, which that was one of the things that surprised them. And then every now and then it would be deflected, but not just a little bit like he thought, like crazy. It would be deflected almost back at him, like with incredibly strong force. So he's like, what is in atoms that, first of all, doesn't have any effect the vast majority of the time, and then when it does have an effect, it's a massive effect? Turns out he had discovered the nucleus. So, conclusions from Rutherford's study. This is what he expected. He'd expect there might be a mild little deflection if it came near an electron because of the charge. Remember, the alpha particle has a charge of +2. And he had this massive deflection. So what that told him, because 99% of the time it went straight through, what that told him is that an atom is made up of mostly empty space, which means the nucleus, although it comprises almost all of an atom's mass, it is so compact and so small in the center. So most of an atom by far is empty space. I've heard the analogy that if you imagine a football field is an atom, just size-wise, that the nucleus would be like a little tennis ball in the middle of the football field. So it's quite a difference there. All right, so Rutherford discovered the nucleus. He knew it was positively charged. The positively charged, that's from the protons we know now. Positive charge of the nucleus was part of the reason that Rutherford's alpha particles, which also had a positive charge, deflected so strongly. We know that like charges repel each other strongly. So not only is the nucleus very dense, and that would be a lot of force in the repulsion, but also the opposite charges. So then came Rutherford's model, the nuclear model. And so we knew he refuted Thomson's model. Remember, Thomson said there were just negative charges, kind of evenly dispersed. That's not true. So the nuclear model says there's a positively charged nucleus, and then around that, pretty far away, outside of the nucleus, are the electrons. So this is just kind of written conclusion for Rutherford's study. Almost all of the atom's mass and all of its positive charge are in the nucleus. Most of the volume of an atom is in fact empty space. And overall, atoms are neutral, just in their natural state, because there are an equal number of protons, which have a positive charge, as there are electrons, which have a negative charge, and the two charges neutralize each other. I hope that didn't show. All right, so in summary, the 3 subatomic particles we know today that are in each atom include the neutron, which only contributes mass to the atom. It doesn't have a charge. You don't need to know the masses in kilograms of any of these. This is just giving an idea of how incredibly minute these subatomic particles are. So scientists actually came up with a new unit for masses related to atoms, and it's atomic mass units, AMU, sometimes shortened to U. And so we call a neutron as having atomic mass number of 1, proton atomic mass number 1. So protons and neutrons have about the same mass. And check out the electron. The mass of the electron is an order of like almost 10,000 less than the mass of the proton and neutron. So for our purpose, we're going to neglect the mass of the electron. That makes life a lot easier in calculations. All right, so now you know the basic structure of an atom. And the next big discovery was an isotope. So what is an isotope? It's very easy to get isotope and ions mixed up, so pay attention to which is which. Isotopes, let me give you the definition first. They are atoms of the same element that have different number of neutrons. Okay, atoms of the same element that have different number of neutrons. What? So what happened was, I can't even remember the scientist that did this anymore, but he shot neon, charged neon atoms through a cathode ray tube, and it turns out that it resulted that the particles that he sent off resulted in two different pathways, and it depended on their mass. So neon atoms, which at the time were assumed to just be uniform and all the same, were found to contain two different, slightly different versions of the same atom. And that's what we call isotopes now. And it turns out that every single element that we know has multiple isotopes. I don't know if you knew that or not. There are some that only have 2 isotopes, and I think there's some that have like over 20 isotopes. So remember, an isotope is, okay, they're all neutral. Atoms in general in their natural state are neutral. So they have the same number of protons and electrons, but the isotopes have different masses. And so that's their primary difference. Now they're present in different abundances, which you'll learn later. Like some of them are a lot more stable, and there's a lot more of them in a sample. All right, so you probably have seen this nuclear notation for elements, where the big X is the element symbol. So gold would be Au, magnesium Mg. So that's what X represents, the symbol that you see in the periodic table. Be careful, because if an element symbol has 2 letters, the second letter is always lowercase. That is important. All right, so these isotope symbols, the superscript is the atomic mass, okay, and let's say mass number. We'll call that the mass number, which is simply, and remember that a proton and a neutron each have a mass of 1 atomic mass unit, right? And so the mass number, represented by letter A, is simply the number of protons and neutrons added together. Z represents the number of protons. Okay, that's also called atomic number. So A represents the mass number. Z represents the atomic number. Okay, remember the mass number is protons plus neutrons. Atomic number is only protons. So how do you get the number of neutrons? Okay, this is set up like a subtraction problem. The number on top is protons plus neutrons. The number on bottom is only protons. So if you subtract one from the other, you get the number of neutrons. So one thing that's really important is that it is the number of protons, or remember that's called the atomic number, that defines an element. It's the number of protons that defines an element. So any atom, ion, isotope, any particle that has 6 protons will be carbon. Okay? So it might have 6 neutrons, may have 8 neutrons, may have different number of electrons if it's a charged particle. But if it has 6 protons, it is some version of the element carbon. So, for example, carbon has 3 isotopes. Remember the atomic number? Number of protons goes on the bottom. And the mass number, which is protons plus neutrons, goes on top. And again, it's set up like a subtraction problem. So if you take the atomic number, subtract it from the mass number, what you'll get is the number of neutrons. So carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, carbon 14 has 8 neutrons. So again, isotopes are the same element, they have the same number of protons, but they differ in the number of neutrons they have, and therefore they differ in the mass. Here's a you try problem. So this is where I tell you to please turn off the video, work this out yourself, and then come back and I will work it out for you. Alrighty, so magnesium, and you're going to want to print out a periodic table and have it handy, or a tab on your computer that's bookmarked, because we'll be using it constantly. So magnesium, if you look on the periodic table, the element symbol is Mg, and the problem gave us the mass number of each of these 3 isotopes, 24, 25, and 26. So now you need the atomic number. How do you find that out? Go to the periodic table. The periodic table is arranged by atomic number, that is by the number of protons for each element. So if you look at it, element 1 has 1 proton, that's hydrogen. Element 2, helium, has 2 protons. Lithium, element 3, has 3 protons, and on and on. So if you find magnesium on the periodic table, you'll see that it has 12 protons, an atomic number of 12. All right, and so to find the number of neutrons, we're going to simply subtract. Right, so we know that they all have 12 protons because they're all magnesium. And unless you see a charge shown on an isotope symbol, if you do see a charge, it'll be in the upper right, like plus or minus, okay? If you don't see that, you assume they're neutral, and that means that the number of electrons equal the number of protons, and that's what makes it neutral. Alrighty. Now, an ion. This is easy to mix up with an isotope. So an isotope were versions of the same element that have different number of neutrons and therefore different masses. An ion, on the other hand, is a charged particle. Okay? So it can have an overall positive charge or it can have an overall negative charge. Okay? And how ions are made is from either losing or gaining electrons. Okay, that's an important definition, remember too, from losing or gaining electrons. So now what happens? For example, this happens to be an oxygen atom. It's a diagram of an oxygen atom. So the nucleus, remember what's in the nucleus are protons that have a positive charge and then neutrons that have no charge. And in this isotope of oxygen, there are 8 protons, 8 neutrons, and 8 electrons. Okay? So in this version, it is neutral because the number of electrons equals the number of protons. So overall, it is neutral. Now, if I remove one of these electrons, what are we left with? Well, let's see. The protons will still be 8, right? We started with 8 electrons, but if I take one away, then we have 7 electrons, okay? So what is the overall charge if I remove an electron? +1, okay? It turns out that an ion that has a positive charge is called a cation, and an ion that has a negative charge is called an anion. So let's look at the structure of an ion and how it's different. It turns out that oxygen, when it undergoes a chemical reaction and becomes an ion, prefers to end up with a -2 charge. So remember we started with 888 when it was neutral. And so an oxygen ion, the most common one, has 8810. So it has 2 extra electrons. So it's pretty easy to figure out. For every electron extra, you have a minus charge. And if we have 2 extra electrons, we have 2 minus. I wonder if I forgot to cross out one of these. 1, 2, 3, 4, 5, 6, 7, 8. No. Okay, whoops. 10 electrons. I'm sorry, not minus. We've added 2 electrons, right? If we end up with a negative charge, we've added electrons. Alrighty, so here's one for you to try. This is a real common problem when you're learning ions and isotopes, just to get a handle on the subatomic particles. So fill in the missing blanks, telling the number of protons, neutrons, and electrons, and the symbol for each of these items. So you're going to need your periodic table so that you can identify what element it is. And then, so turn off the video and come back when you're done and compare answers. Okay, so the first thing I did is I looked up the number of protons, or the atomic number, of cesium and iodine. Okay, so cesium has an atomic number of 55. Iodine has an atomic number of 53. So I can go ahead. Atomic number is the same thing as number of protons, so I can fill that in. And the number of neutrons, just subtract the atomic number from the mass number. Okay. 12, 7. Okay. And so that's the number of neutrons. And let me do that for iodine too. Alrighty. Now, number of electrons. You have to look at the charge. So cesium has a +1 charge. It gets a +1 charge by removing 1 electron. So the neutral cesium started with 55 electrons, same as the protons when it was neutral. But since you removed 1, this ion now has 54 electrons. The iodine shown here has a -1 charge, which means it has an extra electron. So neutral iodine had 53 electrons, but it has an extra one, so it has 54. All right, so then atomic number 55, you can either look up here at cesium, or you can look on your periodic table to see it's cesium. Atomic number 94 is plutonium, way down in the bottom. And so remember, the atomic number is the subscript, so I can put a 55 on the cesium and a 94. Okay, so the mass number needs to go as a superscript. So how do we get the mass number? We add together the protons and neutrons. So 137 is the mass number for the cesium. And what is the mass number for plutonium? 145 plus 94. So 239 is the mass number for the plutonium. Now what about a charge? In order to figure out charge, you need to compare the number of electrons and the number of protons. Okay? Remember that protons have a positive charge, electrons have a negative charge. There's 1 additional proton here, so that's going to end up with a +1 charge. Charges go in the upper right as a superscript. Compare the number of protons and electrons for the plutonium. Protons are plus, so we have +94 minus 90. That's going to give us +4 charge. There are 4 more protons. Okay, so that's it. we'll close in on this one. All right, we're going to end up this PowerPoint by just introducing kind of the overall structure of the periodic table. I want to mention first that the first scientist to come up with any rendition of the periodic table was Mendeleev, back in the 1800s. And he took the elements that were known at the time, which weren't that many, and he lined them up by their mass. Our current periodic table is organized by atomic number, not mass. They're similar, but there are several places where it switches. So anyway, Mendeleev was the first to line the elements that were known at the time up by mass. And when he did that, when he lined them up by mass in a certain order, he found that there were elements that had similar properties. So for example, lithium and sodium had similar properties. Carbon and silicon had similar properties. And so it got the name periodic table. Periodic means something that repeats with a regular pattern. So in the periodic table, it's the properties of elements repeat. So today's periodic table, I think it was Moseley that and really all he did was, instead of arranging it by mass, arranged it by atomic number, the number of protons. And I don't know, there were probably 5 or 6 places in the periodic table where a couple elements switched place when he did that. But Mendeleev had the basic idea. And I guess the important thing to get out of the periodic table, there's a ton of information to get out, but for now, just know the elements that are in the same column or group have similar properties. And the basic categories or divisions of the periodic table is the metals it's shown here in cream color. The nonmetals are blue, and the metalloids are green. So pretty much every periodic table that you'll see has what we call a stair step drawn in. Okay. And so basically we say any elements to the left of the stair step are metals, to the right of the stair step are nonmetals, and elements that touch the stair step are metalloids. Okay. So metals, you know properties of metals, right? They tend to be shiny, they conduct heat and electricity well. Most of the elements are metals. The ones down here are metals too. There are many fewer, it doesn't sound right, nonmetals. And nonmetals, metals are pretty much all solids except for mercury, I think, which is a liquid. But nonmetals can be liquid, solid, or gases. They have dramatically different properties. And then the metalloids have properties that are, as you might expect, someplace in between metals and nonmetals. So each vertical group is called a group. Each vertical column is called a group. Sometimes you'll hear old language call it a family, but most of the time a group. Those are the ones that have similar properties. Each row is called a period. So periodic table, period 1, 2, 3, 4, 5, 6, okay? And group 1, 2, etc. So there are 2 different group numbering systems. It's kind of the old-fashioned way, but you still see a lot of periodic tables with it, that they separate the groups into A and B groups. So all of the groups in the middle here, kind of that are dented down, are called B groups. So 3B, 4B, 5B, 6B, 7, etc. And 1A, 2A, and then skip all the way over here, 3A, 4A, etc. There are some periodic tables, and it's a more recent change where the groups are simply labeled 1 through 18, and it doesn't distinguish between the transition metals in the middle. You should be familiar with these more common group names. Group 1, that's right here, that's alkali metals. Group 2, alkaline earth metals. group 16 or 6A in the old things are, that's the group with oxygen, yeah. Chalcogens, you don't hear that used very often, but the other ones you do. Group 17 are the halogens, so that's like fluorine, chlorine, bromine, iodine. And group 18 are the noble gases, so that'd be like helium, neon, etc. Alrighty, so we talked a little bit about ions, just that they're charged particles, and I do want to emphasize again that atoms in the periodic table are assumed to be neutral unless you're told otherwise, and it's only really when they start undergoing chemical reactions that they may become an ion. But when elements do become ionized, when they gain or lose electrons, they have really repeatable common charges that they get, and the behavior is the same for each individual group. So, for example, group 1 or group 1A, all of the elements in that group, when they become an ion, have a charge of +1. Ooh, how did I do that? Okay. I'm having trouble here, guys. Good thing it's almost over. All right. The elements in group 2 or 2A, whatever, when they become ions, all have a charge of +2. Now, these are the transition metals in the middle, the B groups, and they have variable charges. They're kind of troublesome in a lot of ways, unpredictable. So we're not going to talk about them right now. But if you resume the A groupings and go to group 3A or 13, depending on the numbering system, look at that. Okay, they all have charges of +3. Group 4A, carbon group, doesn't tend to make ions, but when it does, it can be either +4 or -4. The nitrogen group, then -3. The oxygen group, -2. The fluorine or halogen group, -1. And the noble gases do not tend to make ions. And we'll learn more about why that is later. So I want you to memorize this pattern. Here's the pattern. I'm going to write down here because I made a mess on the top. +1, +2, skip the transition metals, +3, plus or -4, -3, -2, -1. You see the pattern? Check out what is the pattern here. So it's kind of like a mirror image. Okay, think of the carbon group as like the halfway point if we're ignoring the transition metals. And so you have +1, +2, +3, and then on the other side of the carbon group, -3, -2, -1. So you'll be using that a lot later, so it's good to commit that to memory. Oh, yeah, this is better than my little drawing. Alrighty, so here's some really simple questions you might be asked about the periodic table. So if I asked you what element is in group 13 and in, what if I just said period 3? Group 13 and period 3. All right, so it go period 1, period 2, period 3, so it's in this period, and it's group 13. All right, so that is aluminum. All right. So what is the element in group 16 that has the smallest atomic number? So that'd be on top, right? That's oxygen. Okay. The third row or third period, I won't be using rows, I'll be using period. The third period metalloid. So you may have to draw probably have to memorize the metalloids because it can get confusing otherwise. There's the stair step, and the metalloids are elements touching the stair step except for aluminum. That's considered a pure metal. Okay, so the third period metalloid. So the third period is sodium, And so that would be silicon because aluminum is a pure metal. And then the fourth row, alkaline earth metal. So the alkali metals were group 1, the alkaline earth metals were group 2. So it's important to learn these. So fourth period, so that's 1, 2, 3, 4. And then the alkaline earth metal is calcium. So to make cement, the elements used are aluminum, oxygen, calcium, and silicon. And that is it for Chapter 2.